Okay, next talk will be given by Yuan Fang from Rice University.
Okay. Yes, thanks for the introduction. Yeah, so I will be talking about the strange metals and entanglement weaknesses. This is in collaboration with many people at the Rice, including Rachel, Monica, Mahakali, Yiming Wang, Dr. Fang Xie, and Professor Ximiao Si, and also Dr. Hui from the Northern Institute and Professor Silke Fischel from TU. So I will be talking about the strange metals. Strange metals usually appear around the quantum distraction quantum critical point. And this QCP is said to be beyond the Landau's paradigm of quantum criticality because there's a localization, delocalization transition labeled by this dashed line here. So this transition has no obvious order parameter to describe it. Therefore, it is beyond the Landau's framework. And therefore, new means are needed to study the QCP and the strange metals. So here we want to do so by introducing entanglement quantity to study the QCP and the strange metal. And this is the entanglement weakness, which is our quantum fission information. So with this in mind, I will start by introducing quantum fission information. I will discuss where the name comes from and why it is an interesting multipartite entanglement. And then I will review the Kondo effect and the Kondo lattice and discuss our findings in this model. And then I will discuss what's the new insights it brings us about the strange metallicity. And finally, I will briefly discuss the QFI for Fermi liquid. Entanglement is a very important concept in quantum mechanics, and it's almost everywhere in fundamental physics. We say a state is entangled if it's not separable. The separable states are defined as those whose density matrix can be written as a classical mixture of product states. So here are two examples, the product state and the classical matrix states, they are separable. And entangled states are those cannot be written in this form. So for example, a Bell state is entangled and it cannot be written into this expression. And the entanglement measure that quantifies the amount of entanglement is actually a very broad topic. And here I only mention this most commonly used entanglement entropy, which is defined as the von Neumann entropy of the reduced density matrix. So we know entangled states can have stronger correlations than the separable states. So let's focus on our bipartite system. We have subsystems A and B, and then we can define local operator OA, OB that acts strictly on the subsystems. And then the connected correlation is defined by this formula. So we can actually use the connected correlation function to classify the states. So if for all the local operator, your CAB is equal to 0, then we actually have uncorrelated product states. But if CAB is non-zero, we have two situations. The first one is the separable states with classical correlation, and the second one is the entangled states. And to distinguish them, we usually need some further entanglement measure like connectivity and entanglement of formation. So this figure is schematically showing the relation of the three cases. And for the pure states, actually the subregion between uncorrelated and separable will collapse. For the pure states, all the correlated states, they are entangled. So this is a hint why entanglement is encoded in correlation. And we know the entanglement entropy and other entanglement measure are very hard to be detected in experiment. And in history, the first accurate measurement of entanglement is actually through the Bell's inequality. And this has led to the Nobel Prize in 2022. So what the Bell's inequality tells us is that we have a two-qubit system, and we can measure the correlation of the local operators on the two qubits. Then there's a bound for a certain combination of the correlation function. So for other separable states or classical states, this correlation must be smaller than 2. So if your measured correlation is beyond this bound, then you have witnessed the entangled states. So this is why we say the Bell's inequality is actually an entanglement witness. And the key features to construct the entanglement witness include, so first we need to have correlation of local operators, which essentially is measurable. And second, we need to have a bound for the correlation function, which can help us distinguish entangled states with separable states. But the Bell's inequality is only a bipartite entanglement witness, and there's actually a multipartite entanglement weightiness that works for many body wave functions. It is the quantum feature information. So let me formally introduce the quantum feature information. So firstly, the name quantum feature information actually comes from the metrology theory. So it basically tells us about the amount of information we have about estimating a parameter. So you can also see this is a quantum results about the estimation problem. So there's a theorem called the quantum Cramer-Rawle lower bound, saying that the uncertainty of your estimation for a parameter theta is lower bounded by this inverse of quantum feature information, which is defined by this formula. So here, lambda is the eigenvalue of your density matrix, and theta is a parameter you want to estimate. So basically, this expression is measuring the sensitivity of your state with respect to the parameter theta. So you can see the larger the quantum feature information, the more precise your measurement or estimation will be. And one important property of QFI is that it is always greater than the classical feature information. And the classical feature information has been defined for the classical estimation theory for a long time, and it is well known in their community. So, so what this means physically is actually the entangled states have more information than its separable states. Yeah, so this is where the name comes from. And why it is an interesting quantity to condensed matter physicists is really because this is actually also a multipartite entanglement and it is measurable. So now I'll explain what this means. Let me actually first define what is multipartite entanglement. So we first should define a state is unproducible if it can be written as a classical mixture of the product states. And here, each patch, rho I, has at most m particles. So such states are called unproducible. And a state is called unpartite entangled if it is unproducible but not m-1 producible. And it has another name, which is the entanglement depth equals to m. And this is a concept borrowed from the quantum circuit theory. So for example, the Bell state is two-partite and the GHZ state can be three-partite entangle. Okay. Quantum feature information actually provides a lower bound for the entanglement depth. And this is realized by considering a special estimation problem about the parameter encoded in a unitary transformation e to the minus I theta times O. And here O is a formation operator associated with your parameter. And in this special case, your quantum feature information can be simplified into this form. And here, the lambda is a eigenvalue of your density matrix. And you need to further consider your operator to be a sum of the local operators. And in this case, you can prove that the QFI per particle is bounded by the integer m for all the unpartite entangled states up to some normalization factor. So this means if you measure the QFI greater than m, then you have witnessed at least m+1 partite entanglement. So this figure is showing for our finite system size, what this bond looks like. The dashed line is the bond we are showing here, and then the solid line is the actual tight bond. And here are some examples for QFI for the pure states. So for pure states, they reduce to just the connected correlation function. Or equivalently, you can see it's measuring the fluctuation of the about the operators. And then here are some examples for a qubit system. For product state, QFI is always trivial, smaller than 1. And for W state, it's smaller than 3. And for the GHZ state, it can be as large as n, which is the maximal possible value. And this is in agreement with the fact that the GHZ state is actually a maximally entangled state. And the last, but maybe the most important property of QFI is that it is actually measurable. So QFI is related to the dynamical susceptibility of the operator O that you choose. So they are related by the integral of chi double prime, the imaginary part of the dynamical susceptibility with the tangent H kernel. And I think we have heard a lot from the last talk that the spin QFI can be measured by the neutron scattering experiments. And I'll just quickly summarize here. So basically, you can measure the dynamical spin structure factor, and you can use fluctuation dissipation theorem to get the chi double prime, and then you integrate along one omega direction, and you get the QFI density. Okay, so in summary, the quantum field information comes from metrology theory, but it is useful for condensed matter physicists because it's a measurable quantity that tells you the lower bound for multi-particle entanglement. And there are also many interesting directions related to QFI, including the many-body quantum geometry, but we don't have time to touch on that today. So next, I will apply the quantum fission information to strange metals. The system we study for strange metal is the Kondo lattice model. So let me first review the Kondo effect and the Kondo lattice, and then present our results. The Kondo effect is describing the screening of local moment by conduction electrons. So in a Kondo lattice, we have F electrons coming from the rare earth atoms and all the actinized atoms, and those F electrons are highly localized, and they behave just like a local moment at high temperature. And those local moment is coupled to the conduction electrons through a Kondo coupling, which is an antiferromagnetic type interaction term. So the Kondo coupling is responsible for the Kondo effect and the formation of heavy quasi-particles. And the other important interaction in the Kondo lattice is the HOQE interaction. This is a long-range antiferromagnetic interaction among the local moments. So HOQE interaction will tend to make the local moment to form magnetic order. And this is the Hamiltonian for the model. We use I to represent HOQY and JK to represent the Kondo coupling. If the Kondo coupling dominates, then we are in the Kondo screen phase. So in this phase, the ground state is a Kondo singlet formed by local moment and the conduction electrons. And the quasi-particle excitation by adding or removing one electron to the system is actually creating quasi-particles that are dragging the local moment. So the effective mass can be very large, and the quasi-particle weight can be as small as 10 to the minus 3. So this very heavy quasi-particle actually set the stage for the breakdown of quasi-particle and the emergence of strange metals. And on the other hand, if the HOQE interaction dominates, then we are in the Kondo discharge phase. And in this phase, the local moment form magnetic order. So there's no Kondo effect, so no heavy quasi-particle at all. And in conclusion, in the Kondo lattice, we have a competition between the Kondo coupling and the HOQE interaction, and there's a phase transition between the Kondo screen phase and the Kondo discharge phase. And it also suggests an interplay between the Kondo entanglement and the spin-spin entanglement. So this is the phase diagram of the Kondo lattice model, and the phase transition we mentioned is actually a quantum critical point. So this QCP, firstly, it is a paramagnetic to antiferromagnetic transition, as we have mentioned, but it is more than that. It is also a localization-delocalization transition, which is labeled by this dashed line here, the E local star. So what this means is in the Kondo screen phase, the F electrons are delocalized. They form heavy quasi-particles and they contribute to the Fermi surface. So you will get a large Fermi surface that counts both the conduction electrons and the heavy quasi-particles. And in the Kondo discharge phase, the F electrons are localized. So they do not contribute to the Fermi surface, and you only get a small Fermi surface that only counts the conduction electrons. Therefore, across this transition, you will see a sudden change of the Fermi surface from large to small. And this has been observed in many experiments. So this is the reason why this QCP is said to be beyond the Landau's paradigm. So the quasi-particle here does not just break down at some hot spots in the brane zone, but instead the entire Fermi surface gets destroyed at this quantum critical point. And above this QCP is our strange metals. The strange metals are captured by their linear in T resistivity, the Planckian scaling of the dynamical susceptibility, and also the loss of quasi-particles. So as we said, the strange metals and this Kondo destruction QCP involve both the magnetic transition and the localization-delocalization transitions. So this means there will be a singular spin dynamics and also charge dynamics corresponding to the two transitions. So let's first look at the spin dynamics. So this figure is showing the experimental measurement of the dynamical spin structure factor So the vertical axis is actually the dynamical spin structure factor multiplied by t to the alphas. Here our alpha equals to 0.75, which is the scaling dimension. And the horizontal axis is omega over t. So this is showing our omega over t Planckian scaling for the dynamical spin susceptibility. And there's also a charge sector dynamics. So this figure is showing this optical conductivity. The vertical axis is again the real part of the optical conductivity multiplied by t to the alphas, and alpha is also around 0.75. So this is actually showing the omega over t Planckian scaling of the optical conductivity, which is responsible for the charge degrees of freedom in the localization delocalization transition. So we conclude that this condo destruction QCP is beyond the Landau's quantum criticality because of this transition has no other parameter to describe, and it also suggests that there is a deep spin charge entanglement because of this interplay between spin and charge dynamics. So this is the motivation why we want to study the entanglement in the condo lattice model and for the strange metals. So the method we use to solve this quantum lattice model is the extended dynamical mean field theory. So what the eDMFT does is it calculates the local correlation for the quantum lattice model by using an impurity model called the Bose-Fermi-Kondo model. The Bose-Fermi-Kondo model have the local moments coupled to a bosonic bus and a fermionic bus to represent the RKQ interaction and the Kondo couplings. So we can use an impurity model to solve this Kondo Bose-Fermi-Kondo model. And then we can self-consistently calculate all the 2-point and 4-point correlations in the original lattice model. So with all this information, we can calculate quantum phase information and the mutual information for our quantum lattice model. So let's actually first look at the mutual information. So the mutual information here we studied is for a single site, and the two subsystems are the local F electron spin SF and the local conduction electron SC. This mutual information is actually measuring the Kondo entanglement of the Kondo singlet. So if we get a large mutual information, then this means we have a strong Kondo singlet and it favors the formation of the heavy quartz particles. Here are our results for the mutual information at different temperature, and the horizontal axis is the RKQI interaction. So we can see when RKQI interaction is 0, we actually have a maximal mutual information equal to 2 log 2. So this is saying the mutual information is capturing the Kondo entanglement, which is the 2 log 2 is the Kondo the singlet limit. This is the maximum possible value. So mutual information captures this Kondo entanglement in the Kondo screen phase. And the dashed line is a quantum critical point. And then we can see when we increase RKQI interaction, the mutual information decreases smoothly, and it does not go to 0 even in the Kondo discharge phase. This is showing there's some remaining Kondo correlation even in the Kondo discharge phase, and this is called the dynamical Kondo effect. So mutual information reveals the Kondo entanglement, and it distinguishes the Kondo screen phase with the Kondo discharge phase. But the mutual information does not capture the entanglement at the quantum critical point. So this motivates us to start thinking about the quantum phase information. The quantum phase information we studied here is a spin QFI. So the operators we define is actually the local F electron spin operator. And we can use this formula to compute the quantum phase information. And the chi double prime is a spin dynamical susceptibility, which can be calculated from eDMFT. So as a reminder, this spin QFI is measurable in experiment, and it provides a bound for the multipartite entanglement. So here are our results. So this calculation is for low temperature, and the figure is showing the normalized QFI density versus different RKQI interactions, and the dashed line is the quantum critical point. So we can see this normalized QFI density is trivial in both the Kondo screen phase and the Kondo discharge phase. which means they are not witnessing any entanglement in those two phases. But close to the QCP, it is sharply peaked. So this is showing an amplified entanglement appear near the quantum critical point. And the value of the peak is around 2.2, which means it has witnessed at least a three-partite entanglement. So in this sense, we say the spin QFI characterizes this condo destruction quantum critical point. Then let's look at this temperature dependence. So now we look at the QCP, the QFI at this QCP, but with different temperature. So we can see the QFI density decreases when you increase temperature. This is expected because we know thermal fluctuation can destroy the quantum entanglement. But the point here is this QFI remain to be non-trivial in an extended range of temperatures, which is the regions of the strange metals. So notice the lower value for the y-axis is 1.4, so it's still non-trivial. So this is showing the amplified entanglement in the strange metal. And our results are supported by the experiments. So these figures are showing the unnormalized QFI density. The left panel is from our EDMFT calculation, and the right panel is from a recent experiment on this critical condo heavy fermion. And we can see they have a similar temperature dependence, and the maximal value for the QFI density are comparable. So what does this amplified entanglement witnessed by the spin QFI tell us about the strange metals? So we say there's amplified entanglement witnessed at this QCP and in the strange metal phase. And we want to say that this is a consequence of the long-range RVB-like correlation in the strange metals. So this is very different from the condo spring phase where your local moment forms singlet, and also different from the condo discharge phase where your local moment are ordered. So here in the strange metals, the local moment can fluctuate significantly, and they are entangled with other local moments among multiple sites on the lattice. So this is a multipartite entangled state. And the second, we want to say that the entanglement among the F local moment is detrimental to the condo effect. So, the large QFI witnessed here demonstrates the breakdown of the condo effect. And so it blocks the formation of the heavy quartz particles. So in this sense, we say the QFI is uniquely suited for the condo lattice model, and it characterizes the loss of the quartz particles. So in summary, I've introduced the mutual information and the quantum fission information for the quantum lattice model. The mutual information captures the condo entanglement, and the quantum fission information captures this condo destruction quantum critical point, and it extends to the strange metals. And there's an interesting perspective from entanglement. In the perfect condo limit, we have a condo singlet, and according to the theorem called quantum monogamy, the local moment cannot entangle with other local moment because it's already maximally entangled with conduction electron spin. But near the quantum critical point, the quantum singlet is weakened by the RQI interaction, so the local moment can fluctuate and entangle with other local moment on the lattice. So this is showing our transfer of the entanglement from condo entanglement to the spin-spin entanglement, and this is characterizing the loss of quasi particles in the strange metals. And there's still one subtle question. So we know the Fermi liquid should actually be highly entangled. Then why is a heavy quasi-particle Fermi liquid phase spin QFI being trivial? And can any QFI capture this entanglement? So this motivates us to study the general question about QFI in Fermi liquid. And I will show you that we can actually prove all the local operator QFI will be trivial, and the non-local operator QFI may be capturing this large entanglement in Fermi liquid. So Fermi liquid has a large entanglement because it has a logarithmic violation of the Aver law. This means its entanglement entropy grows faster than the Aver law. And so we ask the question, what operator of QFI can we use to capture this large entanglement in Fermi liquid? So firstly, we can show other fermionic operator or the Majorana operator cannot do this job because of the fermion statistics. And second, we will show the local bosonic operators cannot do this work either. But we will then show some non-local bosonic operators can witness the large entanglement in Fermi liquid. And there are, of course, also some other proposals, including the double system and the 2-IDM. I think we probably will hear this from the next speaker. So for a single band metal, we actually have a simple proof why the local spin QFI is trivial. So this is rather straightforward. This is using the Cauchy-Schwarz inequality, and we can show the maximal QFI density is equal to 1, and the equality only holds at the nesting condition. So we confirm this prediction with a one-band two-dimensional time model. And actually, this proof can be generalized to any fermion bilinear local operators and for multi-band systems. And the conclusion does not change. We also tested the interaction effects on this local QFI. So we studied a 2D Hubbard model, and we choose a parameter carefully to avoid the slowness instability so that we are still in the Fermi liquid phase. And we use RPA to calculate the spin dynamical stability and then calculate this QFI density. And then we can see the QFI density is indeed enhanced by the interactions, but it's still quite finite. So it's still not capturing the large entanglement in the Fermi liquid. Then we think about the question, what about the non-local operators? Yeah, so the study of the non-local operator is motivated by the Jordan-Wegener transformation. Jordan-Wegener transformation maps the local fermionic operator to spin operators, or the hard-core boson operators. And those hard-core boson operators, they commute at a different sites and anti-commute at the same site. And you can verify that they still satisfy the requirements of using QFI as entanglement witness. So we studied this non-local spin QFI for 1D single band metal and also a two-ladder model. And we can see that this normalized QFI density scales with the system size polynomially. So it diverges in the thermodynamic limit. So it's showing a very large entanglement in the Fermi liquid. And currently, we are still exploring ways to measure the proposed non-local QFI, for example, in the cold atom systems. Okay, so to summarize, I have discussed the mutual information and the quantum Fisher information in the quantum lattice model, and also the strange metals. So and also discuss the local and non-local QFI in the Fermi liquid phase. Okay, so thanks for your attention. I would like to acknowledge my collaborators again, and I would like to take any question.
Thank you. Time for a couple of short questions, comments.
Thank you for the talk. It's really exciting to see these theoretical models being applied to QFI. The question I have is on this kind of picture that you drew, where you see quantum Fisher information peaked at the quantum critical point, but it goes to a very small value within the antiferromagnetic phase. And generically, you'd expect the QFI to be something larger when you're talking about entanglement between spins. Is this because of the wave vector that you've defined that you're probing QFI? Or is this because EDMFT does not capture the entangled nature of an antiferromagnet?
Yeah, that's a good question. Yeah, I think we have tried all the wave vector Q for other cases, but still not seeing our large QFI for the antiferromagnetic phase.
I guess Yuan has only shown SZ.
Long range.
Yeah.
Very strong.
Yeah.
Fluctuation.
SX and SY are more complicated to calculate. Any other questions? Comments? We're just about getting to the cutoff time. So thank you again.